My psi k was pointing over there. This new one will point at an angle. Yes? Think of the 2D, nothing more. This will point at some different angle. It will not point towards psi k. It will not stay there. My state of the system gets changed. Yes? That's all. So, and it can get changed by this particular amount. It can go to any of the position eigenvalues, any of the position eigenvectors, right? With the probability of Cm square. It can go to any of those. So, and that's my uncertainty, that it can go to any of these positions with these particular probabilities. Because my momentum is completely defined, my position is completely arbitrary. Right? Okay. Fine. Well, let me tell you, in the very beginning, sometimes it gets a bit confusing, but when you start thinking about it, it's a very beautiful concept, because you start thinking about these multi-dimensional spaces and going from one space to the other. Yeah? Huh? Sorry? So of course, the other way around is also. That will be completely arbitrary. Yes. So, sorry? If you define completely the momentum, so if it is in psi k, that means it's in one of the eigenstates. So I completely know the momentum, root 2 MEK. Position is completely uncertain. It can be any of the possible positions. Yes? I'll get any of these positions.
How can you solve for eigenvectors for position?
Sorry?
How can you solve for eigenvectors for position?
You can, but not in this course again. Because that is another thing. I don't know. You'll have to learn a lot more about Fourier transform, Fourier series, Dirac delta functions, if you already know. No. So that's, you know about the delta function. The delta function. Delta ij is equal to 0 if I is not equal to j, is equal to 1 if I equals j. This is for a discrete distribution. The Dirac delta is for the continuous distribution. So anyway, forget it. But just forget it. Okay. I don't think that will need another 5 lectures before I can tell you what is a continuous distribution. That's why I didn't, even with this, I just use a discrete distribution. So I know the value of the momentum. When you measure the momentum, I know the value of the momentum as root 2 m ek. That means it's completely defined. Whatever, if it's completely defined, sure. But if I know the value of momentum, and then I want to measure the value of position, then it's completely arbitrary. No, when I measure only then I'll know. No? 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 No, you will not get it. Huh? Now the thing is that all I was telling you is only one measurement. Right? When I do a lot of measurements, then what I get is a distribution of momentum, which depends on sigma of, if my state is phi, then it depends on sigma of ck square. Sorry? Unfortunately, you don't measure one at a time. Okay? So, more strictly, so let me take it a step forward. More strictly, the uncertainty principle is defined for an average of measurements, not for one single measurement. Okay? I just tried to show you how using the one single measurement concept I can still get my uncertainty principle. But anyway, it's going to be uncertain in any case. But it's defined for an average. Okay, so let me just switch gears and go on to a two-dimensional particle in a box. And the problem is similar. So 0 to A in one direction, 0 to B in the other direction. V is equal to 0 inside, V is equal to infinite outside. So we can write the Schrodinger equation then and solve it. Minus h cross square by 2m. Now I have to worry about motion along x and y. So let's define that as x and that as y. Del square of psi. Now psi is a function of x, y both. Plus del square psi by del y square. So that's my kinetic energy part. Plus potential energy Vxy of psi is equal to E of psi. Right? Now, where do you see cross terms? Do you see any cross terms between x and y? So something like x times y or something where y is a function of x. The partial derivatives are not, indeed. It's only differentiate with respect to x or with respect to y. V of xy could be. I don't know the form of that. But in this particular case, it happens to be 0. When it's infinity, of course, my psi goes to 0. You've seen that. So, the only place where it could have been was inside the box, but it's 0. If it's 0, then I don't have to worry. So, which means that my x and y happen to be independent. If they happen to be independently variable, then I can always write psi like that, in general. Sorry? No, psi is the function that depends on x and y. Okay. So, what I am saying is, if y is not a function of x, if they are independent, yeah, psi does depend on both x and y. So, I can write it. This is the same thing that we did when we separated u of x comma t as x and t. Okay. This can only be done if there is no interdependency of the two variables. They can be varied independently. So if I do that and I plug these values into the Schrodinger equation, minus h cross square by 2n. Now this is an ordinary differential, d square x by dx square times y happens to be a constant for this fellow, plus x is a constant, d square y by dy square is equal to E xy. And then all I need to do is to divide by xy on both sides. And then I take either y or x on the other side. Okay. E is a constant. So, the left hand side happens to be a function of only x, the right hand side happens to be a function of only y. that has to be equal to some constant. Let me call this constant as Ex for convenience. Then I can write my equation as minus x cross squared by 2n d square x by dx square is equal to Ex times x, and the right hand side I can write as minus h cross square by 2m d square y by dy square is equal to Ey times y, where Ey happens to be, or Ex plus Ey happens to be E. Yes? No? Yes, no? And these equations I know. The boundary conditions are the same.